Good afternoon, class. In today's video, what I'd like to do is to go over another version of the second law of thermodynamics, because while the second law can be written as delta S equals delta Q over T, it also can be written in words and expressed in words in another way. And I thought and they cover the same thing. It's just that what I wanted to do was to show an example of how that works, and with a couple of real-world examples. So the second law of thermodynamics can also alternatively be explained as heat will not flow spontaneously from a cold reservoir to a hot reservoir. Now, of course, what is a cold reservoir? What is a hot reservoir? That's a good question. We know what heat is because in the last video, I did define it. So I won't go into that one today. But a cold reservoir is some place where heat can go, where energy can travel from, so a place where there's a lot of energy to a place where there's lower energy. So for example, from a hot coffee mug, a cup full of hot coffee into the air. That would be the cold reservoir, which would be the air. Another example, even just biologically, your lungs have air at about body temperature, and so when you breathe it out, it's going from a hot reservoir to a cold reservoir outside of your body. So those are some ways that this can happen. Now, the reason why I want to go over that is because this is a way that the first law and the second law work together. So, and you can actually see this in cars as well. So we'll get some of that. We'll get to that one in a little bit. So in this case, you have a hot reservoir, and heat will flow down into a cold reservoir. That is normal. That is what we call, it can do it spontaneously. It's one of those laws of the universe where you don't need to do anything to the system to make energy flow from hot to cold. You do have to do something to get it to flow from cold to hot. That is different, and we'll cover that in an example too. But in example one, what happens is you have high energy or something that's hot, and it's going into something that's cold. Heat is being transferred, obviously, because there's a transfer of energy, but you can also get work out of that system. So an example of this would be the car engine, the engine in your car. Because when the spark plug ignites the gas, so there's the fuel injector, and it injects fuel into a small place into the compacted site of the pistons and the engine, and then the spark plug fires, it ignites that gas, and the gas pushes on the piston, and those pistons are one piston that gets forced down, and that forces the one next to it. So one goes down, the other one goes up, and they're mechanically connected to each other, and that's why when one goes down, the other goes up. When the second one goes up, it gets smaller, so that when the spark plug fires again, that one can now go down and the first one comes up. So there's work being done because there's actual mechanical motion going on from the piston and from the engine of the car. All that is because energy is coming from that tiny little explosion of fuel, or the ignition of fuel that's pushing on the piston of your car engine. So one way that some people have told me in the past is that a car engine is basically an explosion that happens really, really slowly. So it's something to think about, because there are mini explosions in your car engine all the time, and we don't find that at all dangerous. We just find that normal. That's just how an engine works. So, but you do get work out of it because, as for any of you who have ever ridden in a car or any kind of vehicle that's been powered by an engine, you get mechanical work out of it because you go to the place that you need to go. The car moves. So that's great. Now, we'll go on to example two. So that's a car engine. This one, what is this? Can you actually get cold, energy? And don't get me wrong. I should probably clarify this too. Something that is a cold reservoir is only cold because it has a lower energy level than the hot reservoir. Okay, so it's not like this has no energy and this has energy. This doesn't. This still has energy. It just has less than this one. Oh, and so I'll finish this one up. So for this one, we would take a look and say, okay, so how could you possibly do this? You can get something cold and pull energy from that to a hot place. So basically, you're making something colder. You're taking a cold thing and making it colder, and you're taking a hot thing and making it hotter. That doesn't actually make a whole lot of sense. And for those of you who have ever been camping and roasted marshmallows over a fire, you should know that what I'm talking about, because you've never seen somebody throw water onto a fire and have the fire become even bigger and the water freezing. You've never seen that, because what happens is when you throw water onto a fire, the fire goes out, right? That's normally what happens. So that's why this example doesn't seem to make sense. You can't throw something cold like water onto a hot fire and expect the water to have energy sucked from it and it turns to ice. That doesn't make any sense at all. However, it does make sense if you can put work into the system. So essentially, if you go from hot to cold, you can get work out of the system. But if you go from cold to hot, it is possible, but you have to put work into the system. So an example of this would be your air conditioner. Anytime you use the air conditioner, you've basically taken a room and you've made it colder by cooling down the air and pumping that air into the room. Where does the hot air go? Because you must have heated something else up. That gets pumped out. Another example is your refrigerator or your freezer, right? It's all of those places are much colder than the surrounding room temperature. And if you've ever gone to your refrigerator or freezer and you felt the back of it, like so if this is your refrigerator and you felt the back of the refrigerator, it's always really hot back there. And that's simply because you're putting in work to pump the cold air and make it colder into the hot air, which is the outside, the room temperature air. So those are some examples of how the second law of thermodynamics plays out, and hopefully that helps you visualize in your everyday life too, where you see the second law of thermodynamics actually playing out. So that concludes the alternative, the secondary version of how to read the second law of thermodynamics. Good luck in your studies, and may the force be with you.